Okay, so hello everyone. I'm very happy to host Roi Livni that will talk about can implicit bias explain generalization. So Roi, the stage is yours.
Okay. Okay, so I'll try to talk about, actually it's based on two works. One is more recent. The first is with Asaf Dauber, Meir Feder, and Tomer Koran, and hopefully if I'll have some time, then I'll also discuss a second work about PAC-based learning, which is a joint work with Shai Moran. So the importance of implicit bias in learning, it's kind of a classical viewpoint or a common wisdom that when you want to learn or when you want to feed a model to some set of observations, then what you would like to do is, in some sense, choose the simplest model or have some bias towards less complex models. So it's manifested in the saying by Occam or Occam-Razor, which basically says that you should always choose the simplest explanation. And you can also think about it in more modern time as a result of Vapnik-Chervonenkis that says that when you want to feed a model, you want to choose it from a small set of models, which is measured by what is known as the VC dimension. And there are basically two ways today you could think of it. In theory, you kind of have these two strategies for model fitting. One of them says that you have data and you want to feed a model, so you basically choose from a small set of models any one that fits your data. So for example, you do polynomial interpolation, you have 10 data points, so you feed some curve or some function through these points, and you can basically feed one degree polynomial or 2 degree polynomial, and that would make sense because the number of parameters in your model is less than the number of examples, so you expect that you will not overfit. Obviously, it doesn't make so much sense to feed a 10-degree polynomial, an arbitrary 10-degree polynomial through a set of 10 points.
I'm not hearing you very well. Is it just my problem, or is it everyone?
No,
I think the problem is, yeah, I think it's with Roi's internet.
Roi, maybe shut down the video, and so only the audio will be okay, and then it will be less.
Now can you hear me?
Yes, now it's better, I think.
Can anyone hear me?
Yes, we're hearing you okay.
Okay, so maybe when I'm far, that's the problem?
I don't know, try to talk and we'll see.
Okay, so I'll try to talk close. So like I said, so far we just talked about the fact that you want to fit a model to a problem. One strategy would be to choose a model with less parameters, the number of examples, and that would make sense. And there's another approach that says if you want to feed a model that has much more parameters, number of examples, and what you usually do, you can regularize, which can effectively be thought of as basically reducing the effective number of parameters. But if you say you want to fit a 10-degree polynomial to a set of 10 points, then...
Again, you don't sound very well. Maybe try to close the video and just keep the audio. I think it's internet problem and not just sound problem.
Okay, so let's try that. Okay, now it's better?
Yes.
Yeah, I think so.
Okay. Okay, when I'll make faces, then I'll put the video back on. Still better or just...
Yeah, it's better.
Yeah.
Okay. So again, so you want to feed a model, let's say with 10 parameters, 10 number of examples, and what you usually do, you would regularize the complexity. For example, you would put some regularization, norm regularization over the weight of the coefficients of the polynomial. And then you also achieve some objective generalization. But this trend or like the observation, maybe sometimes it just works to perform fitting of the interpolation of your data, even when the number of parameters is larger than the number of examples. Now, I think the polynomial example shows that it's just a characteristic view. It's
Roi, maybe can you try talking into a microphone, or I don't know if you have like any earphones that has a microphone in it or something.
I got
technical difficulties.
בוא ננסה. יותר טוב?
בינתיים כן, תתחיל לדבר ונקווה שלא נחסר אותך.
כן, אוקיי. So there is this common late observation that, you know, if you look at how modern machine learning algorithms are working, it seems as if what they do is basically they just feed the data, whether the number. Still hear me or?
Yes, you're good now.
If the number of, you still feed the data.
Maybe we can return to video.
Or small. Now, obviously, when you look at this polynomial interpolation task, it seems almost a characteristic way of viewing the thing. But this is kind of the best view, or the best way we now know how to describe what is being done in the case of neural networks or even random forests and many important and modern machine learning algorithms. So there was this work by Neishabur et al. In 2015 and also Zhang et al. In 2017, who noticed that when you learn a neural network over your data and you use some algorithm like a stochastic gradient descent, then in fact, making the model more complex and with more free parameters, not only does it not ruin your test accuracy, but in some sense it even helps. And this is done even though no regularization seems to appear in the formulation of the problem. Okay, and this kind of leads to the question, what's going on? How can we explain generalization in these complicated models? So can you still hear me?
Yes, you're okay.
Okay, I thought you just all went away. Okay. So by the way, questions so far? Or? Okay. So what's going on? So obviously, if you look at the picture of the polynomial interpolation, it's cannot be that what we're doing is some naive interpolation of the data, because that cannot work. But even though the current situation is that if we look at large-scale problems, the common practice, the best practice even, is to fit large models to small data sets. So here small means compared to the size of the model. They are considered big data, but the models are even bigger. At least explicitly, no type of regularization seems to appear. So something needs to prohibit the overfitting of the model, okay? And then came this idea or this viewpoint that says maybe what's going on is that there is some sort of what we would call implicit bias or implicit regularization, which basically says that when you consider the problem, then okay, maybe there is no explicit regularization in the way you formulate the algorithm, but the algorithm does do certain steps. It does work according to some rules. So maybe the code or the exact solution that this algorithm chooses, that induces some sort of regularization, which maybe we don't know of, but exists there. So inherently, there is some regularization that appears implicitly in the algorithm that we are running. Okay? So people, I guess most of you have heard of implicit bias and implicit regularization, right? Can you still hear me, by the way?
Yes, yes.
Okay. Maybe I'll put back the video or?
Yes, definitely.
Okay. So if now there's still internet problems, then let me know and I'll stop the video. Not that the video is that important. Okay. So this is implicit bias. So just let me give a few examples. So what can go on, or how can, like, toy examples to implicit bias. So I think the best example is, it's very toyish and it's very simple, but I think it exemplifies the idea behind implicit bias quite remarkably. Let's think of the case of linear losses. Okay, so here is a task. You observe x's coming from some distribution D, unknown distribution D. And what you want to do is you want to choose a parameter W where it minimizes the scalar product with x. So you want to minimize the expected value of W dot x. Okay, linear problem, very easy, we all know how to solve it, and nothing special about it. And then you can look at an algorithm like stochastic gradient descent. So what does stochastic gradient descent do in this setting? How does it optimize the problem? At each iteration, you choose you choose iteratively W's, and W at step t+1 is going to be the former W minus eta xt. So you move from your previous model to some model which is slightly better in terms of the empirical observation of this point. Okay, so you iteratively always improve, and you can prove that this algorithm has some guarantees. I don't want to go into what are the exact guarantees, but at least allegedly, if you look at the algorithm, it doesn't do any sort of regularization. It just consecutively improves its solution and greedily takes a step towards a better solution. However, the same algorithm can be written in a completely different form, where we would call it the follow the regularized leader, where you say that at step t, the algorithm chooses Wt to be the minimizer of a regularized objective, which includes a trade-off between the empirical risk and a term of L2 loss with factor 1 over eta, where eta is a step of the algorithm. Okay, maybe you've seen the equivalence between these two formulation. Maybe you haven't. It's really not that hard. You just take the derivative to find the optimal solution to this equation, and you see that it is exactly the same parameter. So these are basically just two different ways to write stochastic gradient descent for linear losses. And once you write it like this, it is clear that the algorithm is biased. It has explicit regularization of L2 node. And you could say that in this form, the algorithm is implicitly biased. Okay, so this is like the dream case of implicit bias. You just can rewrite the algorithm in a way that gives you the bias. Can you still hear me?
Yes, yes.
Yes.
Yes. I guess if it goes wrong, we'll tell you.
What?
If it goes wrong, we'll tell you.
Okay. But I'm afraid that it will be so bad that you won't even be able to tell me that it's bad. So I prefer to ask once in a while to know that I'm not alone in the room. Okay. So here's another example, linear regression. I don't want to go into the derivation, but roughly linear regression, you see x, y's coming from some distribution D. And again, you want to choose W that minimizes W dot x minus y, a well-known task. I'm sure you've all seen it before. And you might want to consider the empirical loss. And it's not hard to see that if you minimize this empirical loss using some algorithm, basically any reasonable algorithm, gradient descent, stochastic gradient descent, then the solution that you're going to converge to is going to be the least L2 norm solution. Okay, from all the solutions with the loss that you achieve, the W that this algorithm is going to converge is going to be the one that has the smallest norm. And this is because the solution will be in the span of the x's, and in that span there is a unique solution, and that solution also has minimal norm. Okay, so these are, I think, the classical example of implicit bias. You think of just the algorithm that minimizes this empirical loss, but if you do it in a certain way, like gradient descent or stochastic gradient descent, then the solution has certain properties beyond just minimizing the loss. They are also the least norm solution or regularized DRM and so on. And like I said, so lately there is this intuition that we should also explain deep networks in this way. So there's been a lot of work lately about this issue, which basically tried to identify the implicit bias in many interesting situations. For example, Daniel Sudri and collaborators in 2017, they observed that if you train a logistic loss over separable data, then the solution you would get converges to the same as the max margin solution. So it's not an L2 regularization. There's no L2 regularization, but geometrically it behaves like an L2 regularization in the sense that the solution that you're finding, if you normalize it, it's up to normalization, it's the same solution as a least L2 norm. So in terms of classification, you basically converge to the same classifier as the least L2 norm. So this is another example, a more non-trivial and more complex example where you can see that by running a certain algorithm, you do get certain implicit bias in the solution. And then there was this list of other work which basically started to identify implicit regularization in practice or in theory in a lot of interesting tasks. In matrix factorization, there's some evidence that you converge to the smallest nuclear norm, and also for fully connected linear networks and for convolutional neural networks. None of these you could find some sort of structure in the solution that might be able to explain the generalization abilities of that solution.
When you say linear networks, you mean without activation layers?
Without activation functions. It's just it's a non-convex problem because you have multiplication between the layers, but there is no. Usually there is no. All of these models they are not as degenerate as linear losses, but they are still. None of them is, I think, about like real deep networks or anything like that. Okay. So what did we want to do in this work? So we said, okay, so let's look at a very specific theoretical setting of stochastic convex optimization, and we said let's see if in this setting we can say something in general, like not a specific result showing that if you run this algorithm on this data, you get this type of implicit bias. But can we can we actually analyze what is the implicit bias of an algorithm like stochastic gradient descent in the setting of stochastic convex optimization? Now, I will explain exactly why we choose this model of stochastic convex optimization and why we choose this algorithm, but I just want to do a recap to make sure that we all know what are these models. So stochastic convex optimization, a very simple setting. You have access to samples from some unknown distribution D. And for every Z, you see a function L, W of Z. And this function is basically parameterized by Z, and it is convex in your parameter, W. And your task is to choose W that minimizes the expected loss, while you need to choose W from a convex set K. Okay, so this setting captures many of the known problems like linear regression and SVM and so on. You choose this Z to be an XY or something like that, but it's a much more general setting, but it basically captures a lot of important problems. And the algorithm we wanted to study is stochastic gradient descent. So also, I think we are all familiar with this algorithm. How does this algorithm work in this setting? You sample a Z from the distribution, and you update WT, where you move from WT minus 1 towards the gradient with a fixed step size eta. And finally, you return the average of your output. Now, there are other variants. You can also return the last iterate. You can do decaying step size. And the reason we choose this model, one, because this is the formulation that is most general in the sense that it works for all convex functions, Lipschitz and so on, but you don't need to assume strong convexity, smoothness, and things like that. And also because actually this is the hardest case. So most of the result, all of the results we are providing would also be true if you look at the last iterate, or if you look at the decaying step size and so on. We don't have these pathological examples where we kind of use some properties of the average or the step size. Okay. So let me go a little bit about why are we interested in stochastic convex optimization. So for this, let's go over other models and what are the possible models to even think about investigating this problem. So there are definitely simpler models, for example, binary classification or PAC learning, and also GLMs, which is a special case of stochastic convex optimization, which captures linear regression and others. What's so special about stochastic convex optimization versus this model is that you could say that this area or this model are where we know that learnability is equivalent to what we also call uniform convergence. In other words, when you want to learn in the PAC model or in GLMs, what happens is that basically, once you have enough data, you can estimate the performance of every model in the class you're trying to learn. And then you can just choose the best one, because all of them, their performance in the test data and in the trained data will be basically the same. In other words, it's not so much, learning in this model is not so much about the algorithm. Nothing in the algorithm really can add much to make it learn better or worse, because as long as the algorithm optimizes the training loss, it will have the necessary guarantees. So studying implicit bias or how the exact algorithm you are using induces a generalization doesn't make much sense in this case. Or in other words, we know what is the bias you need. You need some bias like a small VC, or you need some bias like small Rademacher complexity. And as long as you have this in your class, then the algorithm is less of an issue. Stochastic convex optimization is exactly the area where this stops and things are becoming slightly more interesting. where, so this is a result by Shamir et al. From 2009, I think, where what they showed is that you can actually generate problems in stochastic convex optimization where some performing naive ERM to fit a model to your problem can fail. On the other hand, certain algorithms are still able to learn. For example, regularized ERM, performing empirical risk minimization, but adding some regularization term, will lead to a generalization. But it is about the algorithm. You need some property of the algorithm in order to learn. Just doing naive ERM, just fitting a model, may not be enough. So they generated a problem where this is exactly what's happening. If you just, there are models that have small empirical risk, but do not generalize. But on the other hand, the regularized ERM algorithm will choose a model that will generalize. So this is exactly where things are becoming interesting. And you could say that if the algorithm induces some structure on the solution, then you are learning. And if that doesn't happen, then you shouldn't expect learnability. And of course, there are more complicated models, but usually here we don't even know what is learnable, what is not, what makes things learnable. So it's really hard to start producing results. But I think for this problem, stochastic convex optimization already shows the properties or the non-trivial properties that are enough in order to study the problem. And also, why are we looking at SGD? So SGD has the following two properties, which is exactly what we want. First, it's an algorithm that can learn in this setting of stochastic convex optimization. So we don't need to worry about that. It is a learning algorithm. This is a classical result. We should all know it. And the second property is that a priori, we don't know what its bias. It's not like regularized ARM, where we can say, this is the bias of SGD. So if we want to start investigating how implicit bias helps us to generalize, this is the most trivial, most non-trivial and yet trivial case where things are starting to become interesting. You have an algorithm, it performs some operations. We don't know what is implicit bias, and yet it generalized. We can prove it generalized, so everything is okay. And so the natural question is, what is the implicit bias of SGD in this setting of stochastic convex optimization? Okay, so I want to start with the warm-up question. I want to see what you think. I'm guessing that from the abstract of the talk, you can guess the answer to this question. But as I said, if you do stochastic gradient descent on linear losses or even linear regression, the solution is the minimal norm solution. So this is the implicit bias in those cases for SGD. What do you think if it's a general result? Could you say that if you run a stochastic gradient descent over convex functions, would it converge to the minimal norm solution? So would you like to vote about it? Would you like to just say yes or no? So I know that you're here.
There is just one solution, right?
What?
I said that it must depend on the initial point. If you initialize it
yeah. You're right. So the Euclidean, the least norm solution is from the, so I'm thinking that you initialize it from 0. The more general, if you initialize it from another point, then the closest point to the initialization, that would be, you're right. So you initialize at 0.
Okay.
We can make polls if you want, or
what?
We can make a poll through Zoom, or just.
I can make it, or you can make it.
I don't know. I can.
You want to do it? No, I think by the time that people will even notice that they need to be actually in the talk. Okay, so I'll give you the answer. Don't be too surprised, but the answer is no. You can generate examples where SGD doesn't converge to the closest Euclidean norm solution. It's actually, it's one of the results that you get, and it seems okay, very interesting, nice, but it's just a starting point. But actually, it was the hard, let's say, most of the work we did was on this part to prove this result, and then other results started to stem from it.
Is it also true for gradient descent or only stochastic?
Okay, good. So the next question, what if you do gradient descent? You asked the question, so you need to guess.
Okay, I'm guessing no either.
Yeah. Good. So the answer, yeah, it's no. So not only we're going to show an example where SGD, actually it's gradient descent. And now, what happens if it's a smooth function? Maybe it's not even clear why smoothness should change things. But let me tell you that it does change things. So what are you guessing?
Yes.
No, the answer is still no. It changes things, but the answer is still no.
It's smoothness in the convex optimization way or in the analysis way? Because
no. In the convex there is only the convex optimization sense. What is analysis?
Oh, sorry for questioning.
No, what? I don't know what is analysis. And I'll also say that so in retrospect, we did find that for the case, if you look at gradient flow, is in work by Sugala and collaborators, they did show some examples. They didn't exactly give a proof. They kind of showed a general qualitative result that said that you won't go. What we do here is we give a quantitative result for gradient descent with fixed step size. So this is where we add on this result. Okay, so exactly what can we show? What we can do is we can construct a problem where you would have several global minima. You need that if you want to converge to anything but the closest. And you can make sure that SGD will not converge to the closest Euclidean minimum. So in fact, it's a single function. So I'm saying SGD, but it's actually GD, because you see the same function all over and all over. And there is a certain parameter in the problem where you can basically make the trajectory go to the closest Euclidean norm or to any point here. So in other words, I can make sure that for any function, not just Euclid norm, for any regularizer we suggest, I can make sure that SGD will not converge to the best solution in terms of that regularizer. Let me give an outline of the construction. So the general idea is as follows. So like I said, you need to generate a problem where there are many global minima. So here's a natural way to do that. So this is the set A, and let's say it's just order point 1x, and you start at 0, and let's say that your loss f is going to be the distance from the set A. So just minimum A from A, x minus A, right? Sorry, W minus A. Okay, so this is a simple function. Obviously, I don't think it's very hard to see that the gradient points upwards, and you will converge if you take this function to the closest Euclidean norm. Okay, but at least you have many solutions. So now you can start working. And I guess the natural thing to do is say, okay, so it converges to its closest point. So let's change the closest point. Let's change the metric in which we are considering the point. So let's take some Manabolis metric, and now let's consider a function g that says that your loss is your distance from the closest point, but not in Euclidean norm, but in another norm. So now the closest point is no longer here, is somewhere here. Do you think that will change the way gradient descent behaves? Yes, no? Are you here?
Oh, you're here.
Okay, so at first we thought yes, and then it turns out no. Even though the closest point is here, still the gradient points here. And this is why I wanted to say about smoothness. So why is it happening? So in some sense, it's happening because of smoothness and symmetry of the problem. And I'm saying this because in some sense it does show certain implicit bias. It does show that certain structure in the problem does add bias. For example, in this case, the reason it still points upward is because smooth function have this property that you cannot go too far from the minimal points. So in other words, the trajectory, if it will go here, it will diverge from some minimal point here. And if it will go here, it will diverge from here. So the only way it can go is upwards. So in order to make it not go upward, you need to break the symmetry of the problem. So we replace A with this set. A equals 1x, but x is positive. And now it works. So now the closest point is back here, but the gradient, so you still use the Monopolis distance. The Monopolis distance shifts your gradient towards here, and you get what you want. You get a function that goes like this. And you don't go to the closest Euclidean. Okay? So to summarize, what these results show is that basically for every regularizer, so there is a fine print here. And the reason there is a fine print here is because if you take something like a constant regularizer, then the result doesn't hold because obviously you always minimize some regularizer that doesn't care. So some assumptions are needed, but I would say that they are all just to avoid pathological example like this.
Well, what is
even more pathological example? Sorry?
What is the definition of regularizer?
So okay, so for us, regularizer is basically a function from the parameter space to a positive number. It's like it penalizes. That's all. Now you do need certain assumptions. For example, it's not zero, and some sort of continuity, something even weaker than continuity. But let's think of basically functions from the parameter space to a positive number. And if you want, you can think of continuous functions. Okay?
Thank you.
Okay. So for any regularizer, you can always find some distribution depending on that regularizer, a constant also depending on the regularizer, and a solution where if you compare the output of SGD, where you run it with some fixed step size, where the number of steps is at least 1 over eta, and you should, because less than that you will not converge, then the output of SGD will have the following properties. First, its empirical loss is going to be at least the empirical loss of the candidate solution. And in terms of regularization, it's going to be worse. It's going to have worse regularization penalty. In other words, SGD does not try to minimize, to find an empirical loss that minimizes that regularization penalty. Okay? In other words, you cannot find some distribution independent notion of implicit bias that can explain the behavior of stochastic gradient descent. Questions so far? Okay.
Can you please repeat the last thing you said? It wasn't very clear to me.
So what I said is that you cannot find some notion of regularization that is distribution independent, which explains what the behavior of SGD. SGD doesn't try to minimize some norm like Euclidean norm or whatever norm you can think of. It doesn't find a solution with the smallest norm or anything like that. In general.
Okay, thanks.
Okay. So this leads us to the next step, which says, okay, so distribution independent, that doesn't exist. But what about distribution dependent? So what does it mean distribution dependent? So if you look at the result we have in the literature, then what people know how to show is that if you run on logistic loss, you get one type of regularization. And if you run it on matrix factorization, you get another type of regularization. So maybe, okay, so maybe there is no regularization that is dependent on SGD, but maybe there is this notion of regularization which is incorporated in a problem and the algorithm. So whenever the algorithm runs on a problem that it can learn, then on that specific problem, it has some behavior which is specific to this problem, which makes it generalized for this specific problem. So this is the next step. Okay, so there's no distribution independent. Maybe we can say something about distribution dependent regularization. So here I want to divide the result into two. I'll explain in a minute why. The first case is, okay, so maybe there is a strongly convex regularizer. Why strongly convex? What's so special about strong convexity? First, so this is the definition. Basically, a strongly convex function is just a strong type of convexity, which adds this term to the inequality of convexity. And the reason it's so interesting is because this is the example to how we can show regularization actually induces generalization. It's a seminal result, Bousquet and LSF, which shows that basically if you add a strongly convex regularizer, then you induce some stability of the solution, which can explain generalization. But the division is not exactly to strongly convex and non-strongly convex. The division is to what I would like to call tie-breaking regularizers. So what does that mean? So you can think of two types of implicit bias or implicit regularization. One, like strong convexity, which basically says there is always the best solution. You give him a set of solutions, it can pinpoint one that says, this is my optimal. This is from all these solutions, this is the simplest. This is what strong convexity does. And the second type of regularizer you can think of says, I don't really care what parameter you're choosing, I just want it to be in this set. There is a set of bad solutions, there is a set of good solutions. And as long as you're in the good solutions, I don't really care. It does regularize the problem, but not as strong as strongly convex or tie-breaking regularizer. And the reason we make this distinction is because the type of things that you can say in these two cases is very different. In this case, we can actually show that you don't have some tie-breaking regularizer. It doesn't exist. When it comes to some non-tie-breaking, then it's a little bit fuzzy because you can always say that the set of solutions that the algorithm chooses, that's implicit bias. So here the problem is not so much about saying whether there is or there isn't implicit bias. It's more about saying how does the implicit bias affect generalization. So I'll give the results about this case, and I'll give also results about this case, but they are going to be of different nature.
Can I ask a question?
Okay, can you still hear me?
Yeah. Does tie breaking mean that for any couple it chooses the best one, or is
I'm
this
guessing you can.
transitive or something?
If anyone wants to say yes, that will be helpful.
Okay.
So implicit strongly convex regularizer, the main result we have is that no, there is no strongly convex regularizer. What does it mean? It means that you can find a distribution. Let's say that you run your algorithm with step size 1 over square root t. You run in a problem where the number of parameters is larger, is the same order as the number of examples. So this is roughly the interesting regime. So you can construct a problem where for any strongly convex regularizer, with high probability, the solution that you're going to output, there is going to be another solution which has the same empirical loss, but also better regularization penalty. So again, you are not converging to any regularizer. Now, comparing to the other result, here note that it's the same distribution for all regularizers. Before, we needed to say for each regularizer, I'm constructing a problem. Here we're saying there is one distribution for which all strongly convex regularizers are basically cannot be accounted for the implicit bias of stochastic gradient descent. So here is a construction. It's also not that complicated. So the idea is we start with an auxiliary construction in R2, where we have two losses. With probability half, we're going to show you this, and with probability half, we're going to show you this. So what's happening in this loss? In this loss, the gradient at 0 points upwards, but then there is this regime where the loss is 0. So you can construct this function with something like hinge loss or it's very simple. You can think of a piecewise linear function where in this regime, the gradient is over here, and here the gradient is 0. And another function where the gradient points rightwards, and again, after one step, you move to an area where the gradient is 0. So the main conclusion is that if I show you this function, you're going to reach this regime, which is great. And if I show you this function, you're going to reach this point, which is also great. And it's great for both points. Both of them are points that minimize the empirical loss of each and every one of them. So in other words, let's say I have a regularizer that prefers this point, then with probability half, I'm going to reach this point. And let's say I have a regularizer that prefers this point, then with probability half, I'm going to reach this point. So in any case, no matter what your regularizer says, with some probability, I'm not going to go to the optimal solution in terms of your regularizer, which prefers a certain point. However,
where you are pointing with the mouse, can you point again about the points?
Sorry?
I can't see where are you pointing.
Yeah, okay, so I'm saying, let's say you see this, let's say your regularizer, so your regularizer is tie breaking. It should prefer either this point or this point. Now let's say you have a regularizer that likes this point, then with probability half, you're gonna see the other function, and you're gonna reach this point. So you did not minimize that regularizer. And in terms of empirical loss, both points are okay for both problems. And if your regularizer likes this point, then with probability half, you're going to reach this point. In any case, you're not going to reach the optimal solution with probability 1 in terms of the regularization penalty. However, the only thing about this construction is that the distance between these 2 points is order eta. So yeah, you did not reach the optimal point, but the distance is approximate. You almost reach the optimal point because their distance is very, very small. So if you take large data, you have small step size, this distance is almost negligible. So what do? We just multiply this problem in high dimension, and we make,
Wait.
Yes?
Sorry, but can you repeat this, the last sentence? You were, it was hard to hear you again.
It says your name is Tomer, and I can't hear you.
Yeah, sorry. I asked if you can repeat, if you can please repeat the last sentence. I couldn't hear you again, and I think everybody else couldn't do.
Okay, so repeat it from where?
Just the last sentence.
So what I said is that these 2 points are very close because you're taking small steps. So up to some numerical distance, you are reaching the same point. Okay, they are different, and you could claim that you did not reach the optimal regularizer, but up to eta, you're suboptimal. You're almost optimal. So we want to boost this suboptimality and generate a problem where you reach 2 points that are very far away, and yet they have this property that the regularizer might prefer point A, but you go to point B, or you prefer point B, but you also go to point A. So what we do is we take this problem and we copy it, make T copies of it, and the distribution at each step is going to choose one set of coordinates, and it's going to show you an instance of this problem. And we're going to choose one, either go here or go here. Eventually, basically, you can go to 2 different solutions where these distances are accumulating, and you would get that the distance is going to be order of 1. So that's why you need to also use high dimension. So in other words, what happens is that I constructed a problem where there's actually an exponential set of solutions. SGD can converge to any one of those solutions. All of them have good empirical loss on all possible data sets. So a tie-breaking regularizer will not prefer one over the other. You cannot, none of these solutions is better than the other because you choose arbitrarily from all of them, even though the empirical loss is okay for all of them on all of the problems. So now I want to go to the more interesting case of distribution-dependent general regularizer. So now, sorry, distribution-dependent, but general regularizer. Let's say I don't want to talk about strongly convex. So here I actually use the fact that you can tell me that the regularizer is going to choose one point. So if I can show you that the algorithm goes to different points, then in other words, I can show you that this regularizer is not operating on the problem. In the general case, this is much more complex. And in fact, in the general case, you cannot exclude and say that the algorithm doesn't have some implicit general bias. So far, we showed that there is no implicit strongly convex implicit bias. But if you look at general, then yeah, always, any algorithm, no matter what, has some implicit bias. The algorithm, it's probably harder to construct an algorithm that chooses arbitrary solution, arbitrary ERM solution, than to construct an algorithm that chooses a solution with some structure. And so we can always say that if the algorithm SGD has a set of feasible solutions, then hey, this is the implicit bias of SGD, right? So it always has some implicit bias. So now the question is not whether the algorithm has or doesn't have implicit bias. The question is whether we can say that this implicit bias explains the generalization. So for example, if I take the set of the implicit bias to be the whole universe, I can always say the algorithm converges to some solution. This is the implicit bias. Then okay, but it doesn't answer the question of how does it explain generalization? Why would such an algorithm generalize? More generally, if you do have some implicit bias, but that implicit bias is complex or very big, then it turns up to the question, so how does it explain generalization? So, so this is the next types of results that I want to give. So again, what I would like to emphasize is that here, the results don't show that implicit bias doesn't exist, because implicit bias always exists. It's about what can we say about the generalization properties of the algorithm given the implicit bias. And for this, we introduce this notion of a statistically complex set, where we want to say when is a set of, or when is the implicit bias too large to explain generalization. And we would say that a set K is statistically complex if there is a convex problem where with positive probability, if you see M IID examples, then there is always some solution in this set which would achieve zero empirical loss, but its true error is larger. In other words, performing ERM for a convex problem on this set K is not admissible. Okay, so that's what we would say that a set is very large. And what we want to measure is what is the statistic. If let's say you have a candidate for the implicit bias, you say, here is a problem. I think SGD converges. This is the implicit bias that is operating on SGD in this problem. Then we are looking at the following set. Given a sample S, you look at all this, and you have your candidate regularizer. Let's look at all the solutions that have the same empirical loss as your solution, and they also have comparable regularization penalty. And now we want to measure what is the probability that this set is going to be statistically complex. In other words, we're saying if you have some candidate solution to be the implicit bias of SGD, then this set case that depends on the sample and the regularization should be simple enough so that you could say, yeah, an arbitrary algorithm that chooses a solution from this set should work, because if the regularization captures the reason of generalization, then all the solutions that admit the same regularization penalty should also be considered as valid solutions. So here I would like to stop for questions, because I think this is let's say the most complicated definition we add in this work, which measures what should be considered a non-valid implicit bias. So anyone want to ask questions about this definition, or is this the correct definition?
Oh.
Okay. So I hope it's because everything is very clear and not because nothing is clear.
Most of it
so what is the result
clear.
You can show? Basically, you can take the same construction as before, and you get this interesting result, which says that if you run SGD on that problem that we constructed before, then the set K that depends on the sample and the regularization, no matter what is your regularization that you're going to choose, for any of those, you're going to get a very large set. The set of solutions that minimizes the empirical risk and the regularization penalty, this set is going to be very, very large in the sense that you cannot, in general, perform ERM on it. In other words, just by looking at the implicit bias of the algorithm, just by looking at the set of solutions that this algorithm prefers on this problem, that by itself is not enough to deduce that the algorithm generalizes. It does generalize because it's SGD, but it generalizes because of other reasons. It's not just this implicit bias. You need to know more. You need to know the structure of the problem. You need to know the distribution. You need to know something about the algorithm, because just by observing this implicit bias on itself, that in itself does not induce generalization. Arbitrary algorithms that would choose from the same set might fail on some convex problem, okay? Not on the problem that you are choosing, but on some convex problem. And the idea, we basically reduce the problem to a construction that was given by Vitaly Feldman in 2016. So like I said, in 2009, Shamir and collaborators, they showed that there are certain problems in stochastic convex optimization where ERM might fail. And what Vitaly did, he improved the result. They showed some exponential size, so you need to be in exponential dimension for it to work, and he reduces it to so that the sample is order of the dimension. And he showed that this set, just the hypercube, has this property that performing ERM might fail, but yeah, you could find a solution with small empirical loss, but large generalization. And all we do is we just show that the construction that I showed you before leads to a set of solution which is basically equivalent to this set, up to some linear transformation. So if this set is statistically complex, then our set is also statistically complex. So, okay, so I didn't have much time to talk about the second result. So now if you have questions, then you can ask questions, or maybe I'll just skim a little bit, tell you a little bit about our result in the setting of Puck base, or we can all go our separate ways.
I think you can steal some time.
Okay, so I'll just talk a little bit. This is a new result, still unpublished, about Puck base. So what are Puck base bounds? So they are in the setting of binary classification, and what we consider is some Gibbs classifier which receives sample and they output some distribution over classifiers. And they have this nice result, which says that if you have some hypothesis class that you want to learn, and you have some prior distribution, and you can think of this as the bias of the algorithm. And if you have this guarantee that the posterior of the distribution is going to be close in KL distance to the prior, in other words, the algorithm observes data and then it diverges from the prior to some, so it does some trade-off between being close to the prior or the bias and fitting the data. They can achieve generalization bounds. And what's nice about this framework is that this prior need not be the algorithm can be oblivious to it. So the prior can be, the result is true for any prior, so the prior can be dependent on the distribution as before. And what we show in this result is that for learning thresholds, linear classification on the interval, then basically you can never achieve a pack-based bound. So there is no stochastic algorithm. You can always construct a realizable distribution over the linear threshold, for which no matter what prior you choose, and now you can choose it depending on that distribution. Whenever the algorithm is going to see a sample, then one of two things is going to happen. Either you're going to diverge from the prior, you're going to choose something completely off from your bias, or your loss is going to be almost half. Okay, you're almost going to be as good as random guessing. Where the dependence is in this function phi, which also depends on the interval. So over R, this goes to infinity, which means that this bound becomes vacuous. A little bit about the construction. So basically what we did here is we kind of drew ideas from another work we had with Noga Alon and Mariante Mariales and also Shai Moran. And in that work, we showed certain lower bounds for differentially private algorithms. We show you cannot learn privately the class of thresholds. And basically the idea is the same. Both ideas rely on some instability that you can show. But in some sense, whenever you learn the class of threshold, there has to be some instability. Something very, very small changes in the sample have to lead to very large changes in the output of the distribution. So in other words, any kind of generalization bound that comes from stability needs to fail. So in this work, we basically take the construction we did over there, and we kind of generalize it to show that how, in general, stability arguments cannot be used to prove generalization over a very simple class like the thresholds. Okay, this is all I have to say. Questions?
Thank you.
Okay, thank you very much.
So thank you, Roi. If no one has questions, so thank you again for this great talk. And next week there will not be any talk due to Shavuot, and we'll meet you the week afterwards.
Okay.
Great, Roi, it was very interesting. Thank you.
Yeah, thank you. Roi, are you with us? Because for some reason, oh, okay. So thank you, Roi.
Thank you very much.